Hello Physical Science. We are continuing on with section 2 today, and it is about covalent bonding. So we talked about how mainly covalent bonding yesterday occurs when when electrons are shared rather than transferred. So now we are going to look at covalent bonds even further. So we're going to break down covalent bonds even more today. We're actually going to get two different types of covalent bonds, and there's going to be a little bit of tricky vocabulary, but we're going to try to go over it in class as well in this video to kind of make it a little more clear. So we're going to look at today what happens when atoms don't share electrons equally. So we've talked about how, again with the hydrogen, they are sharing those two pairs of electrons, but we're going to look at other examples where electrons might spend more time near one atom compared to near the other. So it's not really a completely equal relationship here. So some of those other atoms might be a little more greedy and might hold the electrons near them more than the others. And so we're going to have a new term today that has to deal with, again, the location of the electrons, whether or not they are equally shared or not between the two atoms, and that is going to determine whether a molecule is polar. So it has, being a polar molecule has nothing to do with its temperature or whether or not it's a bear. It's just going to be having to deal with the location of the electrons that are formed in a compound. So when atoms form a polar covalent bond, so not just a regular covalent bond, a polar covalent bond, the atom with the greater attraction for electrons will have a partial negative charge, and the other atom has a partial positive charge. So this will make more sense as we go here, but basically when a polar covalent bond is formed, that just means that one atom is going to have the electrons closer to them more of the time compared to the other atom. In a nonpolar, the electrons are going to be shared equally. So we have nonpolar, electrons are shared equally between the two atoms, and in a polar, the electrons are going to spend more time near one of the other atoms, and when you're near one of those other atoms more, you're going to have a partial negative charge because electrons have a negative charge. And the type of atoms in a molecule and its shape are going to be factors that determine whether we have a molecule that is polar or nonpolar. So again, this is going to be a little bit more confusing stuff, so you need to make sure that you're writing this down, you're actually listening to this, so it makes more sense when we get to it in class. So a polar, nonpolar are two types of covalent bonds. So except for noble gases, elements on the right of the periodic table tend to have a greater attraction for electrons than elements on the left. So our 1A, our 2A groups, they are going to have less of attraction compared to, again, to 3 through 8A groups, again, besides the noble gases, so 3A through 7A groups. And then elements at the top of the group tend to have a greater attraction for electrons than elements at the bottom of a group. So that means sodium or lithium will have a greater attraction than potassium because they are both in the same group, but the top ones are going to have more tendency to be greater attraction. So make sure you have your your periodic table in class, and we will maybe go over, we'll add some more to that to make sure we understand where the greatest attractions are going to be, which atoms are going to have the greatest attraction based off of their location on the periodic table, and that will help us determine whether covalent bonds are going to be polar or nonpolar. So polar covalent bonds are what we're going to start with because it's going to be when electrons are shared unequally. So in a molecule of an element, the atoms that form covalent bonds have the same ability to attract an electron, then shared electrons are attracted equally to the nuclei of both atoms, and electrons may not be shared unequally. And I'm sorry, this would technically be describing a nonpolar bond. So this is basically the characteristics of something that's not a polar bond. So this is when they have the same ability of attraction, when the electrons are shared equally to both nuclei, both atoms, and the electrons are not shared unequally. That is a nonpolar covalent bond. So this is like the opposite of a polar covalent bond. So I guess before we get into a polar, they need to actually introduce it. So now here's going to be an example of basically the exact opposite of what was on the previous slide, and it's a covalent compound that forms when hydrogen reacts with chlorine. So a chlorine atom has a greater attraction for electrons than a hydrogen atom does. So that's basically the exact opposite of what was just on the last side. So in a hydrogen chloride molecule, the shared electrons spend more time near the chlorine atom than near the hydrogen atom. And so a covalent bond in which electrons are not shared equally is called a polar covalent bond. So hydrogen and chlorine coming together is what's called a polar covalent bond. Again, it has nothing to do with temperature. I'm sure they have a reason of why they use the term polar, but I don't know off the top of my head. But that just means that the electrons spend more time near one atom, near the nucleus of one atom compared to the other. So in hydrogen chloride, the atoms tend to spend more time near the chlorine nucleus compared to the hydrogen nucleus. So they're still sharing. Again, they both still have that shared pair of electrons, but the electrons are more greatly attracted to the chlorine molecule. And so a couple ways we can actually represent this is right here, and that's the shared electrons in a hydrogen chloride molecule spend less time near the hydrogen atom than near the chlorine atom. And we can tell in this one because right over here on the left, just the bigger space, this just means that the electron spends more time in this area compared to this area. And if you notice over here, the darker area, it means that the electrons are more likely to spend time in this area compared to the smaller, less shaded in area over here. So this is a couple ways to represent the location of the electrons in hydrogen chloride. Again, more space means the electron spends more time there. Again, more space and a little bit darker, actually, you can see, because the electron's more likely to be found there. So that's all a polar covalent bond is. It is just when an electron spends more time near one nucleus of an atom compared to another. And now we're going to look at that's a polar covalent bond. So now we're going to look at molecules as a whole and whether or not molecules can be considered polar or nonpolar. So nonpolar, again, is going to be that the electrons are shared equally. Polar are going to be the electrons kind of play favorites and spend more time with another atom. So can we assume that a molecule that contains a polar covalent bond is going to be polar as a whole? So that's our question, and the answer is going to be all the time no. Just because you have one polar bond does not mean that your molecule is always going to be overall have a polar charge, which again, I know that's confusing, but we're going to do a couple samples here. So more simple solution to this question is that when a molecule has only two atoms, it will always be polar. So no matter what, if there's only two atoms, it's going to be a polar atom. However, when molecules have more than two atoms, the answer is not going to be quite so obvious all the time. And so our example, we're going to look at carbon dioxide and water. So carbon dioxide has polar bonds between the carbon atom and oxygen atoms, and they cancel out because the molecule is linear. So hopefully you can see right in here that this molecule goes straight across. So that's a linear molecule. So those polar bonds will cancel one another out, and overall carbon dioxide is we're going to see be nonpolar, and we'll do these more here in a little bit. Or actually, they get more in depth on the next slide. And in a water molecule, the polar bonds between the oxygen atom and the hydrogen atoms do not cancel out because the molecule is bent. So hopefully you can see here these two hydrogens sticking off don't just go straight across the line like the CO2 molecule does. So in carbon dioxide, there are double bonds between each oxygen atom and the central carbon atom. So oxygen has a greater attraction for electrons than carbon, so each double bond is polar. So initially each of those double bonds is polar. However, the carbon and oxygen double bonds are directly opposite each other, so therefore the pole on the electrons from opposite directions are equal, and the poles are going to cancel out the molecule, and are going to cancel each other out, and as a whole the molecule is nonpolar. So because all of them are straight across one another, again, oxygen does have a greater attraction, but since there's two carbons to kind of balance that out, overall CO2 is going to be nonpolar. However, in water, there are two single bonds between oxygen and hydrogen, and the bonds are polar because oxygen has a greater attraction for electrons than hydrogen, so that's based off their location in the periodic table. However, the water molecule is bent, so therefore the polar bonds do not cancel, and the oxygen side of the molecule will have a partial negative charge, and the hydrogen side will have a partial positive charge. So that's a little bit confusing. We're going to go over that more in depth in class, so make sure if you have any questions, you write them down and let me know. But that's it for this video. We'll wrap up section 2.